The first detection of X-ray emissions from the Interstellar Object 3 Atlas has just been announced, thanks to the extended soft X-ray imaging telescope on board the Japan Aerospace Exploration Agency's X-ray Imaging and Spectroscopy Mission X (RISM). The extended telescope is equipped with an X-ray system that focuses incoming X, combined with an X-ray CCD camera capable of detecting these signals across a broad field of view, measuring 38.5 arc-minutes on each side. The XRISM satellite is also outfitted with the Resolve instrument, which allows for high-resolution X-ray spectroscopy. The newly captured X-ray image illustrates a wide square area of 3 million kilometers per side surrounding 3I Atlas, revealing a faint glow that extends up to 400,000 kilometers from its core. Previously, the first Atlas had only been observed in ultraviolet, visible, infrared, submillimeter, and radio wavelengths. The first instance of X-ray emissions from solar system comets was identified in 1996 with comet Hyakutake, and later confirmed in additional comets. However, up until now, no X-rays had been detected from interstellar objects. With its significant mass and vast coma, Comet 3I Atlas proved to be an ideal target for X-ray observations. The XRISM satellite was able to observe Comet 3I Atlas 1 month following its brightest perihelion phase on October 29, 2025. During a time when it was obscured by the sun and invisible to Earth-based satellites, XRISM is only able to monitor the skies at angles greater than 60 degrees from the sun, necessitating the precise scheduling of its observation of 3I Atlas from 2320 UTC on November 26 to 2038 UTC on November 28, aggregating a total exposure time of 17 hours. During this observation, 3I Atlas drifted slowly through the Virgo constellation, prompting the satellite to adjust its altitude 14 times every 3 hours in order to maintain its position near the center of the extended field of view. A preliminary analysis of images focused on 3I Atlas revealed a faint X-ray glow that extends over an angular scale of 5 arc-minutes, corresponding to a distance of 400,000 kilometers from the object itself. This observation indicates that the bright X-ray halo is likely linked to the gas plume surrounding 3I Atlas, which had been detected by both the Sphere Space Observatory and the James Webb Space Telescope in August 2025. A plausible natural explanation for the detected signal involves emissions from the gas plume interacting with the solar wind. When charged particles from the solar wind collide with the particles in the gas cloud, X-ray emissions result from these interactions. Indeed, the spectrum captured by the extended telescope displays excess emission components related to carbon, nitrogen, and oxygen, alongside background emissions from the Milky Way and atmospheric emissions from Earth. This serves as a critical indicator that the observed emissions may originate from charge exchange interactions between the gas surrounding 3I Atlas and the solar wind. This groundbreaking detection of X-rays from an interstellar object is likely to spark further studies by other research teams. It would be particularly fascinating to determine if any additional characteristics of the X-rays differ from the expected patterns of charge exchange reactions with the solar wind. The discovery of X-ray emissions introduces a new layer of complexity to the enigma of 3I Atlas. While charge exchange with the solar wind provides a viable natural mechanism, it necessitates the presence of substantial amounts of gas around the object, contradicting earlier classifications that deemed it a depleted or dry comet. The detection of sufficient quantities of carbon, nitrogen, and oxygen to produce observable X-ray emissions suggests that 3I Atlas is far more active than previously thought. This situation adds another piece to the intricate puzzle surrounding this interstellar visitor. The inaugural observation of X-rays emanating from an interstellar object marks a significant milestone within the field of astronomy. This finding not only enhances our understanding of the diverse array of objects that traverse our solar system, but also supplies a new method for investigating the composition and behaviors of these enigmatic cosmic travelers. The ongoing revelations from 3I Atlas, coupled with its unique visual features and energetic emissions, perpetuate inquiries regarding its true nature and origins. Below is a list of physical inconsistencies that collectively undermine the comet explanation, with each point elaborated upon further. These include intrinsic X-ray emissions, a rigid frontal jet and antitail directed toward the star, a weak coma and tail with barely visible matter, an anomalous metallic composition, an unusually high nickel-to-iron ratio, strongly negative optical polarization, non-gravitational acceleration lacking a commensurate visible cloud, minimal mass loss inconsistent with extensive jets, and rotation and elongation signals that don't align with a fractured ice nucleus. Additionally, there are repeated orbital coincidences involving passages by Mars, Venus, and Jupiter, an unusual pattern of brightness variations, and blue tones of jets columnated over millions of kilometers. The energy requirements involved are incompatible with the estimated size of the nucleus. The initial point, X-rays detected at the location of 3I Atlas are indicative of intrinsic energy emissions, rather than light reflected from the parent star of our solar system. For a comet to consistently emit X-rays, it would have to eject massive amounts of gases that, during interactions with the stellar wind and particles, would produce such radiation, an exact opposite of what we observe with 3I Atlas, which appears remarkably dry and minimally active. The second point concerns composition. Studies reveal a nickel to iron ratio of approximately 10:1 within the observed metallic fraction, resembling industrial alloys more than the typical composition of a comet's nucleus, which usually consists of volatiles and refractory grains in vastly different proportions. This chemical signature by itself raises considerable red flags. The third point focuses on morphology. A distinct antitail projecting forward, along with columnated jets and a rigid frontal structure, does not align with the expected model of the diffuse ejection of volatile materials. Natural jets usually tend to disperse and show similar colors and compositions when originating from the same source. In contrast, 3I Atlas displays jets with varying tonalities, suggesting a level of heterogeneity that is challenging to reconcile with a homogeneous ice nucleus. The fourth point examines non-gravitational measurements indicate velocity changes that cannot be accounted for by gravitational forces alone. In comet models, these non-gravitational accelerations typically arise from the sublimation of volatiles, which creates thrust. However, this results in a mass loss and a visible debris cloud. In the case of 3I Atlas, we see acceleration without any corresponding cloud that justifies the magnitude of the change, signifying inadequate visible mass to explain the observed effects. The fifth point addresses energy considerations. The extensive, columnated jets suggest mass flows and an energy absorption capacity far exceeding what could be supported by a nucleus of 3I Atlas's estimated size if it were merely ice. Practically speaking, the combination of observed material and ejection velocity would necessitate energy sources or propulsion mechanisms inconsistent with typical cometary physics. It's crucial to emphasize that any isolated point may have alternative explanations. However, when numerous anomalies accumulate, such as excess nickel, frontal jets, negative polarization, unexplained acceleration, irregular photometric activity, and orbital coincidences, the overall picture shifts dramatically. The likelihood that all these factors can be explained through a combination of ordinary natural causes dwindles rapidly. It is the very convergence of these various signals that acts as scientific validation. Traditional scientists who may have initially rejected radical hypotheses are beginning to acknowledge that the most plausible explanation cannot simply be that of a comet. This is not merely an opinion, it is a rational response grounded in empirical observations.